Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature.
Chapter 1 Electric Charges and Fields 1.1 Introduction. All of us have the experience of seeing a spark or hearing a crackle when we take off our synthetic clothes or sweater, particularly in dry weather. Have you ever tried to find any explanation for this phenomenon? Another common example of electric discharge is the lightning that we see in the sky during thunderstorms. We also experience a sensation of an electric shock either while opening the door of a car or holding the iron bar of a bus after sliding from our seat. The reason for these experiences is discharge of electric charges through our body, which were accumulated due to rubbing of insulating surfaces. You might have also heard that this is due to generation of static electricity. This is precisely the topic we are going to discuss in this and the next chapter. Static means anything that does not move or change with time. Electrostatics deals with the study of forces, fields and potentials arising from static charges. 1.2 Electric charge. Historically, the credit of discovery of the fact that amber rubbed with wool or silk cloth attracts light objects goes to Theis of Miletus, Greece, around 600 BC. The name electricity is coined from the Greek word reprint 2025-26. 2 Physics rods, like charges repel and unlike charges attract each other. Figure 1.1. Meaning many such pairs of materials were known which electron amber on rubbing could attract light objects like straw, pith balls and bits of papers. It was observed that if 2 glass rods rubbed with wool or silk cloth are brought close to each other, they repel each other. Fig 1.1a. The 2 strands of wool or 2 pieces of silk cloth, with which the rods were rubbed, also repel each other. However, the glass rod and wool attracted each other. Similarly, 2 plastic rods rubbed with cat's fur repelled each other. Fig 1.1b, but attracted the fur. On the other hand, the plastic rod attracts the glass rod, Fig 1.1c, and repel the silk or wool with which the glass rod is rubbed. The glass rod repels the fur. These seemingly simple facts were established from years of efforts and careful experiments and their analyses. It was concluded, after many careful studies by different scientists, that there were only 2 kinds of an entry, which is called the we say that the bodies like electric charge. Glass or plastic rods, silk, fur and pith balls are electrified. They acquire an electric charge on rubbing. There are two kinds of electrification, and we find that I and II, each like charges repel, unlike charges attract other. The property which differentiates the two kinds of charges is called the of charge. Polarity. When a glass rod is rubbed with silk, the rod acquires one kind of charge and the silk acquires the second kind of charge. This is true for any pair of objects that are rubbed to be electrified. Now if the electrified glass rod is brought in contact with silk, with which it was rubbed, they no longer attract each other. They also do not attract or repel other light objects as they did on being electrified. Thus, the charges acquired after rubbing are lost when the charged bodies are brought in contact. What can you conclude from these observations? It just tells us that unlike charges acquired by the objects neutralize or nullify each other's effect. Therefore, the charges were named as and by the American scientist Benjamin Franklin. Positive-negative by convention, the charge on glass rod or cat's fur is called positive and that on plastic rod or silk is termed negative. If an object possesses an electric charge, it is said to be electrified or charged. When it has no charge, it is said to be electrically neutral. Electric charges and fields. 3am simple apparatus to detect charge on a body is the gold leaf electroscope, Fig 1.2a. It consists of a vertical metal rod housed in a box, with two thin gold leaves attached to its bottom end. When a charged object touches the metal knob at the top of the rod, charge flows onto the leaves and they diverge. The degree of divergence is an indicator of the amount of charge. Try to understand why material bodies acquire charge. You know that all matter is made up of atoms and / or molecules. Although normally the materials are electrically neutral, they do contain charges, but their charges are exactly balanced. Forces that hold the molecules together, forces that hold atoms together in a solid, the adhesive force of glue, forces associated with surface tension, all are basically electrical in nature, arising from the forces between charged particles. Thus the electric force is all-pervasive and it encompasses almost each and every field associated with our life. It is therefore essential that we learn more about such a force. To electrify a neutral body, we need to add or remove one kind of charge. When we say that a body is charged, we always refer to this excess charge or deficit of charge. In solids, some of the electrons, being less tightly bound in the atom, are the charges which are transferred from one body to the other. A body can thus be charged positively by losing some of its electrons. Similarly, a body can be charged negatively by gaining electrons. When we rub a glass rod with silk, some of the electrons from the rod are transferred to the silk cloth. Thus the rod gets positively charged and the silk gets negatively charged. No new charge is created in the process of rubbing. Also, the number of electrons that are transferred is a very small fraction of the total number of electrons in the material body. 1.3
Welcome to the Explainer. Okay, today we are diving headfirst into one of the absolute coolest, most mysterious forces all around us. We're talking electricity, but, not the stuff humming through your wall outlets right now. We're looking at those silent, invisible charges that just sit there perfectly still, building up until, bam, they violently leap into action.
I mean, picture this. You're taking off a sweater in a dark room during dry weather and suddenly you hear that sharp crackle, or even see a tiny spark. Or maybe you're sliding out of a bus seat, you reach out to grab the metal door handle and zap, a sudden sharp shock, right? We've all been there. These aren't just annoying little glitches in the matrix. They're literal electric discharges firing right through your body. The charges just pile up from the everyday rubbing of insulating surfaces, and today we're absolutely going to decode the everyday mystery of how and why this happens.
So to really understand what's actually happening when your car door attacks you, we need to talk about the science behind it, electrostatics. Basically, this is the study of forces, fields, and potentials that come from static charges. And the key word to remember here is static. It just means something that does not move or change over time. So instead of dealing with a continuous, flowing current of electricity, we're dealing with electric charges that have piled up and are just sitting there, perfectly still, basically waiting for a path to discharge.
All right, let's jump into Section 1, Tracing the Spark, the History of Electric Charge. Okay, let's dive into this. To really get a handle on how these built-up charges work, we've got to play historical detective for a minute. The very first documented sighting of static electricity goes way back to around 600 BC. A Greek philosopher named Thales of Miletus noticed that if he rubbed a piece of amber with some wool or a silk cloth, suddenly it started pulling in light objects. You know, pieces of straw, pith balls, or tiny bits of paper. And for literally centuries, people just thought, what a weird quirk of nature. But eventually, after tons of careful studies, scientists realized there wasn't just one type of electrification happening here, there were actually two distinct kinds. And it wasn't until the 1700s that the American scientist Benjamin Franklin finally stepped in and gave these two charges the names we still use today, positive and negative.
And here is a super cool fact for you that connects our modern world straight back to those ancient Greek observations. The actual word electricity, it literally comes from electron, which is simply the ancient Greek word for amber. It's kind of wild to think that ancient philosophers rubbing fossilized tree sap gave us the entire vocabulary for the modern electrical age.
Which brings us to Section 2, Two Sides of the Coin, Positive and Negative Polarity.
Now, what's really interesting about this is how scientists actually figured out those two distinct types of charges. It all came down to experimenting with everyday materials. They noticed that if you rub a glass rod with silk, the rod acquires one kind of charge and the silk gets another. So Benjamin Franklin basically established a convention. He decided to just call the charge on the glass rod, or on cat's fur if you use that instead, positive. On the flip side, if you rubbed a plastic rod with fur, the plastic got a totally different charge. So he termed the charge on that plastic rod, or on the silk cloth, negative.
Out of all those careful rubbing experiments, we got what we can basically call the golden rules of polarity. These literally dictate how every electrified body in the universe interacts. Rule number 1, like charges repel each other. So two positively charged glass rods will push away from each other, and so will two negative plastic rods. Rule number 2, unlike charges attract each other. Bring that positively charged glass rod anywhere near the negatively charged plastic rod and they pull right together. And rule number 3, unlike charges completely neutralize each other upon contact.
Now that last part, neutralization, is absolutely fundamental. See, when you rub that glass rod with silk, the glass becomes positive and the silk becomes negative. Because they're opposites, they attract. But here's the fascinating part. If you bring that electrified glass rod right back into direct contact with the exact same piece of silk it was rubbed against, boom, nothing. They no longer attract each other. They stop attracting other light objects entirely. All that acquired charge is totally lost. They basically nullify or neutralize each other's effects, and the objects go straight back to being electrically neutral. All right, moving on to Section 3, Seeing the Invisible, the Gold Leaf Electroscope.
So far, we've only really talked about forces you can physically feel as the shock or see as a tiny spark. But how do scientists actually measure these charges in a lab? Well, the answer is the gold leaf electroscope. And this brilliantly illustrates the whole concept. It's a wonderfully simple little apparatus designed specifically to detect static charge on a body. It consists of a vertical metal rod sitting safely housed inside a box. And attached right at the very bottom end of this rod are two extremely thin, delicate leaves made of real gold. Here's how this brilliant little gadget works. Step 1. You take an electrified object, let's say our trusty, positively charged glass rod, and you touch it right to the metal knob at the top of the electroscope. Step 2. Because the metal rod is a conductor, that electric charge immediately zips straight down the rod. Step 3. The charge hits those two thin gold leaves at the bottom. And since both leaves receive the exact same type of positive charge, they follow our golden rule of polarity. Like charges repel. Because they repel, the two delicate little gold leaves instantly push apart and diverge.
So the crucial point is this. The degree of that divergence, how far those leaves swing apart, is actually a direct visual indicator of the amount of electric charge. If the object only has a tiny static charge, the leaves just push apart a little bit. But if you touch a highly charged object to that top knob, those gold leaves are going to fly wide apart. It's a real game changer because we have successfully taken an invisible static electrical force and turned it into a measurable physical visual cue.
Now, as we wrap up, I want you to really think about this. The source material points out that literally all matter is made of atoms and molecules. Even when materials seem perfectly electrically neutral, they are packed with immense amounts of positive and negative charges that are just flawlessly balanced. I mean, the forces holding molecules together, the forces keeping the atoms of a solid object in one piece, the adhesive force of everyday glue, and even surface tension, all of these are basically electrical in nature, coming directly from the interactions of these charged particles. So if these hidden static charges are responsible for everything from a sudden spark on your sweater to literally holding the atoms of your chair together, what other invisible electrical forces are shaping your world right now? I really hope this explainer sparked a bit of curiosity for you to look at the physical world in a whole new light. Thanks for hanging out with us, and keep exploring.